Hello, welcome you again. Now we start looking at lag design using Rootlocus. Now here plot is given to us is g of s, that is 2 divided by s plus 5 and s plus 9. K of s that I have to design is a lag design that has k, gain, z lag. Why I need to design lag control? Because of design specification. First is overshoot is less than 0.08 or 8%. Second, steady state error for step input is reduced 5 times compared to the proportional control. So what this means? This means that if I calculate the error with respect to lag controller, that must be 1/5 time of the proportional control. Now first of all, I pick this specification, that is maximum overshoot, and calculate zeta using this formula, that is log mp square divided by log mp square plus pi square, that becomes 0.60. so zeta becomes 0.63. Similarly, I have to find sigma d. So because where I want to put my controller key, so it's very easy to find out that gain controller. For that case, what I did, I picked the position of these poles, that is -5 and -p, and take the average. So this will give me the sigma d, the real part that I need for gain controller to calculate the proportional control. So sigma d is -5. Now move to next one. Mu d is omega d. So that is using formula, that is trigonometric formula, that's modulus of the sigma d, then tan of cos inverse of zeta. So zeta is already calculated using this specification, so I put it, so it becomes 8.7. Now desired port location for gain controller becomes -5 plus minus 8.7 J. Now desired point I select is Q is -7.87 J. So now first step is to design proportional control. Normally people call it as P controller. So this means that K of S must be equal to K. So how I do it? So it's very easy. I use the Rootlocus technique of the magnitude, that is K G of S must be equal to 1. So I use this at point S equal to Q, that is my desired point. So when I put the values here, so it becomes K, okay, and the plant was 2 divided by S plus 5 and S plus 9. So now I take the modulus and put equal to 1, and I to calculate K as Q. Now from here, when I do a little calculations, K modulus of K at S equal to Q, and Q is -7 and plus 8.7 J. It becomes S plus 5 times S plus 9 divided by 2. So put S equal to -7 plus 8.7 J. Now when I solve it, K becomes 40. Now this is my proportional control designed. Now next thing is to calculate the error. So error proportional control, okay, because this is due to step, this must be equal to 1 plus K proportional KP for proportional control. So now I have to find KP. So formula of KP for proportional control must be equal to limit when S tend to 0 K time G of S. Now when I put the values here, limit when S tend to 0, K is my 40, and G of S is given to us is 2 divided by s plus 5 and s plus 9. Now when I solve this, the KPRO becomes 1.78. Okay. Now I calculate KP proportion 1.78. Now next thing is to calculate the error. So for error proportion, this becomes 1 over 1 plus 1.78. Now error becomes 0.36. Now this means that because this means that y final is equal to r of t plus error, minus error, yeah, t. So using this, input is step and error is 0.36. so this means the final value with the proportional control become 1 minus 0.36, that's equal to 0.64. Now this is what we have. This is the first design we have to do for proportion. Now we move to next one, and now we have to design the leg controller. Okay, for leg controller, first of all we have to calculate proportion lag, that is equal to 1 over 1 plus kp of lag. But specification given to us is that leg error must be equal to 1/5 time of proportional error. So using this criteria we calculate the error. So we know that leg proportional error divided by proportional error must be equal to 1/5, or if we put the formula here, it becomes 1 divided by 1 plus k p lag whole divided by 1 divided by 1 plus kp proportion. Okay. Alright. Now from here, when I solve it, put the values. So this implies that kp lag become how much? 12.9, right? So 12.9. Now to calculate the lag controller, we need a lag ratio. What is the ratio? Ratio is for kp lag divided by error constant of proportional. Okay. That must be equal to location of lag 0 divided by pole location. That must be equal to, we already calculate lag 1 is 12.9 divided by p, already we calculate that was 1.78. So this implies that z lag divided by p lag is equal to 7.25. Okay. Or z lag is equal to 7.25 p lag. Now here we choose, because lag controller means that you have negative angle, so you have to choose a pole location near to the origin. So in that case, let p lag is equal to 0.1. Okay, this is my design choice. You can have different design choice, but the idea is that lag must be near the origin. So from here, z lag becomes 7.25 multiplied by 0.1, that becomes 0.725. Now doing this, we already calculate the lag controller. So let me write here k of s, that equal to k s plus z lag divided by s plus p lag. That k is already known as 40. Now we have S plus. Z lag calculated was 0.725 and lag was 0.1. So this is controller that we design. Now next thing is lag controller design. Now next thing is lag. Using lag, what is the error? Okay, now first of all calculate error. So error due to lag controller, if you remember, was 1 over 1 plus kp lag. That becomes 0.072. Now final value due to lag controller is equal to R minus error due to lag controller. Error is given to us, so it becomes 1 minus 0.072. Now in this case the final value becomes 0.928. Okay, now angle lag angle contribution. This is the last part to calculate the lag angle contribution. What we do, we just know the location of pole, that is minus 0.1, and location of 0, that is 0.725. Now this is the point Q that we choose where we started, that was minus 7, and let me rewrite here somewhere here. Okay, minus 7 plus 8.7 G. Now this is the point Q. Alright, now I have to draw a line on the pole on there. Now I have to calculate this phi of P lag. Similarly calculate phi of 0 lag. Now I know this line is minus 7 and this maximum is 8.7 G. So now from here, using the triangle, I can say that phi of Z lag is equal to is equal to tan 180 degree minus tan inverse of 8.7 divided by 7 minus 0.725. When I solve this, Z lag becomes 126 degree. Similarly, ZP lag is equal to 180 minus tan inverse, again 8.7 divided by 7 minus 0.1. right, so this become 128 degree. So contribution lag was Z lag minus Z P lag. So Z lag is 126 degree minus 128 degree, and it is minus 2 degree. So we normally have very small angle contribution so that the transient response is not very. So this is the way you can design your lag controller. Thank you.